Welcome to the Peacademia course on the basics of semiconductors. This lecture will cover an introduction to the semiconductor properties. Let's start. By the time you finish this lesson, you'll learn the importance of semiconductors in power electronics, electrical properties of materials, and atom structure. Power electronics converters heavily rely on semiconductor components to process electrical energy. In power electronics, we mainly categorize semiconductor components into rectifying and switching. Examples of rectifying components include diode, silicon-controlled rectifier or SCR, sometimes it is called thyristor, gate turn-off thyristor or GTO, integrated gate commutated thyristor or IGCT, diode and triode. Examples of switching components include metal oxide semiconductor field effect transistor or MOSFET, insulated gate bipolar transistor or IGBT, bipolar junction transistor or BJT, and MOS controlled thyristor or MCT. To manifest why studying semiconductors is of importance when dealing with power electronics, let me provide you with an example. The buck converter is a basic topology in power electronics. Although this converter is so simple in structure, there are already two semiconductor components in its circuit, a MOSFET and a diode. As a designer, before practical implementation, you must make sure that a couple of items are already taken into consideration and calculated. For example, you need to have an understanding of the efficiency or if the semiconductor components are operating in the safe operating area or the semiconductor components are proper to operate at the desired switching frequency. Of course, a smart designer such as you does not practically implement the converter first and then takes care of those I just mentioned. For example, for calculating the efficiency, we need to know the losses in the system. The MOSFET and diode have losses. Generally, the losses in a MOSFET are categorized into conduction, reverse recovery, and switching. The losses in the diode are categorized into conduction and reverse recovery. Anticipating all these losses requires familiarity with the way the semiconductor components work. I hope it is now clear that why studying semiconductors is indispensable. In terms of the electrical properties, materials are divided into conductors such as copper or Cu, isolators such as glass or silicon oxide, and materials that are neither good conductors nor good isolators, semiconductors such as silicon or germanium. You may ask yourself what makes a material to be a conductor, semiconductor, or isolator. Although this question looks very simple but is very fundamental, addressing this question needs us to look deeply into the atomic structure of elements. To start, I need to remind you of some basic concepts from chemistry. Bringing the chemistry to power electronics might sound a bit strange, but knowing the concepts is necessary. When talking about chemistry, the first thing coming to mind is the periodic table of the element. In this table, you can see a list of all the elements discovered so far and their atomic number. The numbers shown in each box are the atomic numbers. The atomic number is the number of the protons in the nucleus. Let's grab an element and see what we can extract from the periodic table. Let's take hydrogen. The atomic number of the hydrogen atom is 1. This means there is only one proton in the hydrogen atom. Let's take another element. This time I grab the silicon atom, the most used semiconductor in the electronics industry. Silicon atomic number is 14, meaning that it has 14 protons in the nucleus. It is best to introduce the atom structure through an example. As a result, I choose the hydrogen atom, the simplest one. We already know that the atomic number of hydrogen is 1. If this is the nucleus of the hydrogen atom, I have 1 proton in it. Since protons are positively charged particles, I put a positive sign right before 1 as an indication. In nature, elements tend to remain neutral, and so atoms. As a result, there must be a negatively charged particle around the nucleus, making the atom neutral. That particle is an electron. The electron has a distance from the nucleus. From the refreshment physics, you may remember that two charges with opposite polarities attract each other. The strength of the attracting force can be calculated by the Coulomb's law. As a result of this force, you may conclude that the electron must attach to the nucleus, but in reality this does not happen since the electron has some energy, keeping its distance from the nucleus. If the electron's distance to the nucleus is bigger, its energy is higher. We often put the electron in an orbit according to the Bohr's model, but what we need to know is that the electrons does not orbit the nucleus similar to the way the Earth orbits the Sun. The orbit represents the energy level at which the electron exists. It is more accurate if we call the orbit the energy level or energy shell. The energy level or shell has a specific meaning. If I say the electron is at an energy level, it does not mean that the electron is at that particular energy level at all times. In fact, 90% of times the electron can be found there. So the electron could be here, here, or even here, but 90% of times here. To make this more clear, let's draw the probability of finding the electron versus the distance. As you can see, at a certain distance, the probability to find the electron is at max. And this is what determines the radius of the energy level or shell. You can also see that with no distance, the probability to find an electron is 0. Here is another example, but a more complicated one. Before I talked about the hydrogen atom structure, here let's talk about the silicon atom. According to the periodic table of elements, the silicon atomic number is 14. So if this is the nucleus, I have 14 positively charged protons in it. Of course, I need to have 14 electrons to keep the atom neutral. But where they are? This is a really interesting question, isn't it? Can I say that I have only one energy level and all the electrons are sitting here? It turns out that this is not correct. So we can conclude that for a more complicated atom, we have more than one energy level, indeed multiple energy levels. Let's ask the second question. This one is even more interesting. Now that I have multiple energy levels, how are the 14 electrons distributed among the energy levels? As an example, can I say I have 4 electrons in the first energy level, 4 electrons in the second energy level, and 6 electrons in the third energy level? Well, the answer is again no. This lecture was an introduction to semiconductors. So far, the atomic structure and energy levels are introduced. In the next lecture, I discuss the energy level in more detail. Thanks for joining another lecture of Peacademia.